This is the third and last part of our lecture on Chapter 6, talking about ionic and molecular bonding. So in today's lecture, we will continue with molecular compounds. We will be talking about the shapes of molecules and how to determine them. Within a molecule, we will talk about the overall polarity of the molecule. From this overall polarity, we will apply it to something called intermolecular forces. All three of these ideas are connected and they build upon one another. One of the main goals in today's lecture is to determine the shape of molecules. The shape of a molecule is very important in dictating a lot of its properties. This in part can explain something like why water, H2O, is a liquid at room temperature, while carbon dioxide, CO2, is a gas at room temperature. So far, we have seen the representation of molecules in a very flat, two-dimensional structure. But in reality, molecules exist in 3 dimensions. So a Lewis structure, although it was very convenient and useful for us, fails to depict the molecule fully. For example, in this Lewis structure of methane, or CH4, it is depicted as a very flat molecule with a carbon in the center and hydrogens equally spaced out in 90 degrees angle. But in reality, the molecule of methane looks like this, with a central carbon atom with hydrogens spiking out from the center. The hydrogens are equally spaced out with about 109 degrees of distance apart, represented neatly in this 3D ball and stick model. Now, it's not as convenient to always draw things in 3D like this with a ball and stick model. So another representation or notation that we have come up with is something called a wedge dash notation. So in a wedge dash notation, everything that is a straight line, like this bond and this bond, that means they are in the plane. Now, what does it mean to be in the plane? When I say something is in the plane, imagine that it is flat. As if you were drawing on a piece of paper, that line would be a part of that piece of paper. Whereas something that is wedged means it's coming out of the paper towards you. Whereas if it's a dash, it's also out of the paper but going away from you. Now the idea to help us predict the shape of a molecule is called VSEPR theory. It stands for valence shell electron pair repulsion theory. And the acronym for that theory is VSEPR. Now, this is a model that tries to help us predict reality. It works most of the time, and as long as you apply it in this class, you will always get it right. Again, this is a model that helps us predict the shape of the molecule based on the number of electron pairs surrounding the central atom. And the basic principle of this idea is that electron groups like to be as farthest away from each other as possible. Remember that electrons are negatively charged. They are similarly charged to each other, so they want to be as far away from each other as possible. Another key component to understanding this idea is knowing what an electron group is. So what is considered an electron group? A lone pair is considered an electron group, and any bond is considered an electron group. Whether that bond is a single bond, a double bond, or a triple bond, that is one electron group. So as you can see, in order to use VSEPR, you must draw the Lewis structure correctly. When you draw the correct Lewis structure, you can see how many bonds are being connected to the center atom, and you can also see if the center atom has any lone pairs in it. I want to emphasize that this theory only cares about the electron groups that is surrounding the center atom. So with the many ways that atoms can connect with each other in a covalent bond, it will result in various shapes. In this class, we will not worry about all the shapes, but just the main ones. Your goal should be to eventually memorize this table. And as you know, my philosophy is to memorize as least as possible, but rather to use logic to help you determine some of these factors. So having said that, let's start on the first one. The first type of shape I want to talk about is when your center atom has 2 electron groups and is connected to 2 atoms. To illustrate this point, our molecule of interest would be carbon dioxide, CO2. From the previous lecture, we recall that as carbon dioxide, the Lewis structure looks like this, with a carbon in the center flanked on both sides by 2 oxygens, and the carbon has a double bond to each of those oxygens. So from this Lewis structure, we can determine how many electron groups is connected to the carbon. How many would you say? Counting electron groups for this carbon, there's one double bond with this oxygen and another double bond with the other oxygen. 2 double bonds counts for only 2 electron groups. Now, if you have 2 electron groups connected to the center atom, how do you think they would be oriented to each other to be far away as each other as possible? You can close your eyes and extend your arms, right? Imagine your fists are the electron groups. Now move them around your 2 arms. In what position do you notice that they are farthest away from each other as possible? Now hopefully you have come to the conclusion that if you hold your arms as straight as possible, almost like in a line fashion, they are as far away from each other as possible. And in that instance, they are 180 degrees apart. So from VSEPR theory, in order to minimize repulsion, when you have 2 electron groups, you will be 180 degrees from each other. This electron group arrangement, because it forms a line, is called linear. The molecular shape is also linear. Now, what's the difference between the electron group and the molecular shape? Now, the electron arrangement is basically the geometry formed from your electron groups, while the molecular shape only counts the shape that is formed from your atoms. In this case, they are both the same because you have 2 electron groups and 2 atoms. We'll see a difference as we move along. So here I have for you represented in 3D this molecule of carbon dioxide. It is a linear molecule with the oxygens farthest away from each other as possible. Again, linear because you can see if you connect the atoms, they form a line. So there you have it. That's our first shape. It's a linear shape when you have 2 electron groups and you have 2 atoms bonded to your central atom. Next, let's talk about what happens when you add another electron group, 3 electron groups. When you have 3 electron groups, there are 2 options where you can have 3 atoms or 2 atoms. Let's first talk about when you have 3 atoms connected only. Our example here is H2CO. And if you properly draw the Lewis structure, it should look like this with the carbon in the center connected to 2 hydrogens and a double bond to the oxygen. So in terms of electron groups, this carbon would have 3 electron groups. Again, counting electron groups, you would say 1 single bond, 1 double bond, 1 single bond. So you will have 3 electron groups. Now think about this. If you have 3 electron groups, how would you arrange them to be as farthest away from each other? Imagine a circle, dividing that circle into 3 parts. What would be the angle of those 3 parts, right? It would be exactly 120 degrees apart. So this electron group is 120 degrees away from this electron group, and this electron group is 120 degrees away from this electron group. This electron group is 120 degrees away from this electron group. Now, again, if you think about that, 120 times 3 would be 360. That's a total angle in a circle. So when you have this kind of electron arrangement, the name for it is trigonoplanar. Trigonal because it's 3, and planar because this is a flat geometry. Imagine if you were karate chopping this molecule. Is there a way when you karate chop it, you can chop all 4 atoms at the same time? If you say yes to that, then it is a flat molecule. It is called planar. And the molecular shape is still trigonoplanar. To help us see again the shape of this molecule, I have here the 3D representation of it rotating. Let's take a look at it and try to see when you can karate chop this, where 4 of the atoms can be touched by your hand at one time. Ready? Should be now or now. You see that whenever you karate chop it at this moment, that you can chop all 4 atoms at the same time. When you can do that, that's something called planar. And if something is planar, that's just a fancy term for being flat. Alright, so now we have covered 2 shapes. First linear, now trigonoplanar. And trigonoplanar is when you have 3 electron groups and 3 atoms connected to it. Now there's a second shape when you have 3 electron groups. You can have 3 electron groups, but only 2 atoms connected to it, and that gives you a different shape. Let's take a look at that example. SO2 would be our prime example in this case. And drawing the Lewis structure for SO2, I would see that sulfur is singly bonded to one oxygen and doubly bonded to another oxygen with a lone pair also. So from this Lewis structure, how many electron groups does it have? Right? We said this was a 3 electron group, so let's count it. A single bond, a double bond, and a lone pair. So 1, 2, 3 electron groups. And so when you have 3 electron groups, how are they oriented from one another? Right? They would be 120 degrees from each other. This electron group is 120 degrees from this electron group, is 120 degrees from this electron group, and 120 degrees from this electron group. Do you remember what this electron group would be called? Right, it would still be called trigonoplanar, again, because the 3 electron groups are all in one plane. Now here comes the difference between this molecule and the previous molecule that we just did. When we talk about the shape of a molecule, we just care about the atoms in that molecule and not the lone pairs. So if you were to ignore that lone pair on top of sulfur, how would you describe this shape? It's basically 3 atoms, but it's not in a straight line. It's rather bent. So the molecular shape of this molecule is bent. Again, its electron arrangement is still trigonoplanar, but the shape of the molecule overall is a bent shape. And here's what it looks like rotating in 3D. You can see the red balls there are the oxygens, and this yellow is the sulfur. And it is in a bent shape. It's not a straight molecule, it's bent. And in this structure, you do not see the electrons being depicted. We just finished the shapes you can get when you have 3 electron groups. You can either be trigonoplanar or bent. If you have 3 electron groups and you're connected to 3 atoms, the shape of your molecule is trigonoplanar. But if you have 3 electron groups but only 2 of them is atoms, then your molecule shape is bent. Let's move on to the next group of shapes. We will now talk about when you have 4 electron groups around the central atom. In the first case, we will have it when we have 4 atoms also connected to it. Our prime example, again, is methane, the molecule I showed you in the beginning of the lecture. The Lewis structure for methane shows that there's a central carbon atom with 4 hydrogens connected to it. And from this, so how would you count the number of electron groups? Right? You would say this is 1, 2, 3, 4. 4 electron groups around carbon. There is a shape that allows for 4 corners to be separated equal distance from each other, and that shape is called a tetrahedron. A tetrahedron is a shape that has 4 identical faces. And it turns out when you are in this shape, the angle between this hydrogen, carbon, hydrogen, this angle right here is 109 degrees. That's as far as each other as you can get. Whereas opposed to just a Lewis structure, you will be tricked by thinking that the farthest you can get from it, if it's a flat shape like this, is only what? 90 degrees, right? This hydrogen, carbon, hydrogen, this angle here gives you only 90 degrees. Whereas this one maximizes it to 109 degrees if you have 4 groups that want to be far as away from each other as possible. So therefore, that electron group is called tetrahedral. And for methane, the shape of methane is still tetrahedral, because if you replace those electron groups with actual hydrogen atoms, it will still have that shape, tetrahedral. So here's what tetrahedral shapes look like in 3-dimensional. All right, are you ready for our first checkpoint? Can you draw the Lewis structure of NH3 and predict its electron group arrangement? Hopefully you were able to draw the Lewis structure for NH3, and it should look something like this. And from this, how many electron groups does NH3 have? It has 1, 2, 3 single bonds and 1 lone pair, so that gives it 4 electron groups. If something has 4 electron groups, what is the arrangement of its electron groups? Okay, so far we've learned about 3 electron groups already. You have 2, 3, or 4. When it's 2, it's linear. When it's 3, it's trigonoplanar. And when it's 4, is tetrahedral. Very good. So that brings us to our next shape. We still are going to deal with tetrahedral for electron groups, but instead of having 4 atoms connected to the central atom, let's see what happens when you only have 3 atoms connected. The previous checkpoint question was to prime us for this example of ammonia, NH3. Again, we drew the correct Lewis structure for ammonia. We have already discussed that there will be 4 electron groups, 3 of them coming from the bonds with hydrogen and 1 from that lone pair. Again, to minimize the repulsion from these 4 electron groups, they will take its shape of the tetrahedron. So the electron arrangement again is tetrahedral. But again, when we talk about the shape of the molecule, we don't consider the lone pairs. So if we have this as the electron group arrangement and ignore the lone pair, we have a molecule that looks like this. From the shapes that we've seen already, there is a shape that is connected to 3 atoms. Remember that? That was the trigonoplanar. But is this molecule planar? Is there a way where you can do a karate chop on this molecule and hit all 4 atoms at the same time? No, right? So therefore, this is not planar. What it looks like is a pyramid. If you consider these 3 white balls as the base of that pyramid, the blue ball will be the top of that pyramid. And so, because of that, the molecular shape is called trigonopyramidal. Again, trigonal because it is connected to 3 atoms, and pyramidal because it's not planar, but it's actually in the shape of a pyramid. This is the 3D rotation of NH3 ammonia. Try to see why this is trigonopyramidal from this image. So again, when it comes to 3D shapes, it gets a little bit complicated and hard to draw. So we like to use the wedge dash notation, where a flat line represents something that's in the plane. A wedge here means the hydrogen is coming at me, and a dash means the hydrogen is going away from me. Alright, so we're almost there. We just finished the shape where you have 4 electron groups but only 3 atoms connected to it, and that was called trigonopyramidal. The last shape we're going to learn today is going down the list, what happens when you have 4 electron groups but 2 atoms. Our poster child for this is actually water, H2O. When you draw the Lewis structure of water, it should look like this. How many electron groups does water have? Again, hopefully you should say 4. It has 2 bonds, that's 2 electron groups, and it has 2 pairs of lone pairs, so that's another 2, so that makes it 4 electron groups. Again, if it's 4 electron groups, what is the arrangement of the electron called? Tetrahedral. Very good. However, when we take a look at the shape of the molecule, can you still call it tetrahedral? You cannot, right? Because those 2 pairs of electrons will be invisible when we talk about the shape of the molecule. Now, what would you call the shape of that molecule then? Think about it. You have 3 atoms. It's similar to what shape we've seen before. Wouldn't you call that a bent shape? And here's what a molecule with 4 electron groups and 2 atoms look like, a bent molecule. So this molecule is planar. You actually don't need this kind of notation to draw it. You can draw with just regular flat lines. Alright, so there we have it. All the shapes. You need to know the electron groups, their names, and what happens when they have different numbers of atoms connected. And from that, you should know the shape of the molecule. You should also know the bond angles associated with each electron group family. Again, you can memorize this, or you can try to use reason to help you remember all of these details. So let's have a checkpoint. What is the molecular shape of PF3? After drawing the correct Lewis structure, you should see that phosphorus is a central atom with 3 bonds, each connecting to a fluorine, and then a lone pair also. So therefore, it is 4 electron groups. However, it is connected to 3 atoms only, so the shape of this molecule would be trigonopyramidal. So the reason why we need to know the shapes of molecule is from the shape of molecule and the idea of dipole bonds we talked about from the last lecture, we can classify the whole molecule as something that is polar or nonpolar, not just the bonds in the molecule, but the entire molecule. And when we talk about polar molecules, you can almost imagine them like magnets. When molecules are polar, they are attracted to each other, and when they're not polar, they are not attracted to each other. And just like how magnets are attracted to each other, polar molecules are attracted to each other from their opposite ends. So keep this image in mind when we talk about the polarity of a molecule. In the same way that we can describe the dipole of a bond, we can also describe the dipole of the molecule. And first, let's talk about when you can have a non-polar molecule. In the first example, we have H2, Cl2, and O2. All of these molecules are non-polar. Can you think of the reason why? So it turns out the first one is that they contain non-polar bonds. In H2, that bond is non-polar because it is connecting 2 identical atoms, which means their electronegativities would be the same, so that bond is nonpolar. Same thing with Cl2 or O2. Whenever they are exactly the same, their electronegativities will be the same, so they will be nonpolar. So if you have a nonpolar bond, your molecule will be nonpolar also. The second way you can have a nonpolar molecule is when you do have polar bonds, but those bonds cancel each other out. And a prime example is CO2, carbon dioxide. Remember from carbon dioxide, that carbon and that oxygen bond is a polar bond. Which one is more electronegative, the carbon or the oxygen? Right? It was the oxygen. So imagine that bond, the electrons are being quote unquote pulled towards the oxygen. Remember, I say quote unquote because nothing's being pulled physically, but that there are just more electrons on the oxygen side. On the other bond, where is that electron being pulled? In the opposite direction. All right, so now if we combine this idea of bond polarity with the shape of the molecule, we can find out that this will be a nonpolar molecule. And why is that again? Remember, the shape of this molecule would be linear, 180 degrees. So if you are 180 degrees completely opposite of each other and you are pulling with the same strength because both sides are oxygens, they will cancel each other out. So this molecule will be nonpolar. In order to spot these occurrences, always look for some kind of symmetry within the molecule. Here's another instance of symmetry. When you have a tetrahedral shape, those outer atoms are all equally spaced from each other. Because they are all equally spaced from each other and they are the same atoms, they will all cancel each other out. Now, if I were to replace one of them, let's say for example, if I were to replace this with a hydrogen, then it loses symmetry, and then that molecule will be a polar molecule. You can imagine, again, using a pulling analogy, this chlorine is pulling it this way and then down, this chlorine is pulling it this way and down, and this chlorine is pulling it to the right and down. They are all pulling down, so overall that molecule will pull down. But in this case, there's another chlorine that's pulling up. So that one up will cancel out with all those small downs. Therefore, this molecule is nonpolar. So I've already hinted when you can have polar molecules. You can have a polar molecule when one end of the molecule is more negatively charged than the other. So in this case, this molecule only has one bond and that bond is polar. If it has only one bond and that bond is polar, then that molecule must also be polar. So more of the electron density is on the chlorine side than it is on the hydrogen side. And as I have alluded in the previous part, the second way you can have a polar molecule is when your polar bonds do not cancel each other out. For example, in this case, water, the oxygen-hydrogen bond is polar, and because of the shape of the molecule, which remember was a bent shape and not a linear shape, if it was a linear, it would cancel. But in this case, it is a bent shape, so this oxygen is pulling this bond this way, and the same oxygen is pulling this bond that way. Notice that they're both pulling upward. Nothing is pulling it down to cancel it. So this overall is being pulled to the top. So we say that the overall, this molecule is a polar molecule with electron density on the top near the oxygen and lacking, where it's a partially positive, near the bottom with the hydrogens. Again, a molecule is polar because it has an uneven sharing of electrons throughout the molecule. Alright, so let's formalize what we just did. I want to emphasize again how to determine the polarity of a molecule. You need to be able to know the shape of the molecule. And again, in order to know the shape of a molecule, you need to draw the correct Lewis structure. So let's try this with H2CO. This is formaldehyde. We've already seen this molecule in this lecture. It has 3 electron groups, so the shape will be trigonoplanar. Now let's think about the individual bonds' polarity in this molecule. The carbon-hydrogen bond is nonpolar, so we will ignore it. And the carbon-oxygen bond is polar, and oxygen is more electronegative. So the polarity of this molecule is towards oxygen, and indeed, this is a polar molecule. Another way of thinking about this is if you were having a tug of war where carbon is in a 3-way competition. Carbon has equal strength with hydrogen, so if carbon and hydrogen are pulling and this hydrogen is pulling, it is not moving anywhere. But in this match here, oxygen is stronger than carbon, so oxygen is able to pull it this way. And if it pulls it this way, the whole molecule is being pulled this way. So therefore, if the whole molecule is being pulled in one direction, we call that polar. Again, nothing is really being pulled or moving around, but it's a good analogy to help us understand polarity. All right, from that, let's have a checkpoint. Which of the following molecule is nonpolar? Let's first do some elimination. We know that HF, option A, would be polar because it is a polar bond, and that's only one bond. So HF should be a polar molecule. And we can cancel out option C because that's an ionic bond, so it's not a molecule actually. So our two options left is B, NF3, and D, CF4. Again, we need to draw the correct Lewis structure, and that's the correct Lewis structure for NF3, and that's the correct Lewis structure for CF4. From this, we can know the shape, right? The shape of NF3, it has 1, 2, 3, 4. 4 electron group is a tetrahedral arrangement, but it has only 3 atoms connected to it, so it's trigonopyramidal, whereas this one is 4 atoms and 4 electron groups. See how it is important to memorize that chart, to know that this is tetrahedral and this is trigonopyramidal. And from this, you can see a tetrahedral shape is very symmetrical, whereas a trigonopyramidal is not very symmetrical because it's missing something on the top. Because of this, only this shape will give you something that is nonpolar, because even though there are polar bonds, those polar bonds will all cancel out. Whereas here, they will not all cancel out because there's nothing to counteract the pulling of these 3 since we're missing an atom on the top. So from that analysis, hopefully you came up with the answer that D, CF4 is your nonpolar molecule. Alright, so all of those ideas culminate into this section, intermolecular forces. And this is a very important idea that can explain to us why this molecule, ethylene, is a gas at room temperature, but if you connect a whole bunch of ethylenes together, it will be a solid. That is essentially what plastic is. Plastic is a bunch of ethylenes all connected to each other. So why would it be that this would be a gas at room temperature, whereas plastic is solid at room temperature? Besides from the properties of materials that we use in everyday life that can be explained with intermolecular forces is also very important in biochemistry. For example, without intermolecular force, our protein will not be able to fold properly. And if your proteins or your enzymes do not fold properly, they will not function. And so as it turns out, these intermolecular forces or attractive forces are determined by whether your molecule is polar or not. So let's first talk about how intermolecular forces determine some properties of a substance. Remember this different state of liquid and gas? Which state had more energy? The gas state, right? In order for a liquid to become a gas, you would have to give energy to this. Given enough energy to this substance, the molecules will break away from the attraction from each other to become gas molecules. Well, that attraction that we were talking about is in this section, intermolecular forces. If you have a high attraction to each other, you would need a lot of energy to break away to become a gas. If the molecules have high attraction to each other, you would have a higher boiling point. If they have a lower attraction to each other, they will have a lower boiling point. Same thing from going from solid to liquid. If they have a high attraction to each other, you would need a lot of energy, so higher melting point. If you have low attraction to each other, you would need lower heat, lower melting point. So keeping that in mind, let's take a look at the attractive forces that exist between molecules. The first intermolecular force I want to talk about is called dipole-dipole attraction. To illustrate this point, let's take a look at 2 molecules, formaldehyde and ethane. These 2 molecules are good for comparison because they have the same mass and the same size, yet different melting temperatures. As you can see here, formaldehyde melts at 181 Kelvin, whereas ethane melts at about 101 Kelvin. Remember from last slide, what does it mean when something has a higher melting point? It must have some stronger attractive force, right? So what is attractive force? It turns out that attractive force is the dipole-dipole force. And it has a dipole-dipole force because it is a polar molecule. A polar molecule, remember, we can also call a dipole. And remember that I mentioned that dipoles are like magnets, and because they are like magnets, they are attracted to each other. So the more polar a molecule is, the stronger the attraction it will have with another polar molecule. And the stronger the attraction, the more energy it requires to pull them apart from one another, resulting in a higher melting point of their overall substance. Whereas if you're a nonpolar molecule, you're not magnets, you don't have that strong attraction to each other, so you don't need that much energy to pull them apart. That's why in the previous section we had to predict whether a molecule is polar or not. From that section we did predict that formaldehyde was polar, whereas ethane is nonpolar, right? It has all nonpolar bonds, so all nonpolar bonds mean the whole molecule is nonpolar. Now let's take a look at another attractive force. This one is similar to a dipole-dipole attraction, but it's a very special type. So to see this attractive force at work, let's take a look at ethanol and dimethyl ether. Among these two molecules, which one possesses this attractive force, do you think? By looking at the boiling points here, ethanol has a higher boiling point. It has a higher boiling point, so it has higher attractive force. So what is this attractive force? It's not a dipole-dipole simply because both of these molecules are polar molecules. So what is it then about ethanol that allows it to have a stronger attractive force? The answer to that is something called a hydrogen bond. And let's first give a definition. A hydrogen bond is when you have a hydrogen connected to a very electronegative atom, fluorine, oxygen, or nitrogen. That hydrogen, which is very partially positive now, is attracted to a lone pair, which is a region of high electron density. So for example, in the molecule of ammonia where you have a nitrogen with 3 hydrogens, this hydrogen is connected to this nitrogen. But the nitrogen's electronegativity pulls the electron towards this way, so this hydrogen is basically partially positive, actually very partially positive. So much so that it is very attracted to the lone pairs that exist on this other nitrogen from the other molecule. This is called a hydrogen bond. It is not a real covalent bond like this bond, but it is an intermolecular bond, an intermolecular force. Inter, again, meaning between two molecules. This hydrogen bond also exists in water. Again, hydrogen connected to oxygen is very partially positive, so it is attracted to the lone pairs of another oxygen atom. Keeping in mind the hydrogen bond that forms from our water here, to apply it back to our previous example. In ethanol, do you see that hydrogen bond? So in ethanol, there is a hydrogen that is connected to an oxygen, whereas in dimethyl ether, there are no hydrogens connected to that oxygen. So therefore, this one cannot have hydrogen bonding. This one only has dipole-dipole, whereas this one has hydrogen bonding, which is a stronger force. And in fact, hydrogen bonding is what allows for proteins to fold properly. Without this hydrogen bonding, proteins in your body will not form shapes that bestows it different functions. And you will see a lot of this example when you take biochemistry courses in the future. Now I wanted to show you an example of such a protein. If you click on that link, it'll bring you to YouTube and you can see this protein at work. This is kinesin. It is a protein that transports materials in your cell. And because of hydrogen bonding, it can have proper folding. And from the proper folding, it would have a proper structure. And without this proper structure, it can't do what it does, which is to walk along this microtubule in your cell and bring the material in different parts of your cell. So the protein that we're talking about is just this one here. And it's carrying this big cargo behind it. Alright, so you can go to that site if you want to see more of this video. It's pretty awesome. Okay, and the last intermolecular force we want to talk about is something called dispersion forces. Now, dispersion forces are the weakest among the 3 forces that we just talked about, and every molecule has it. Even nonpolar molecules will have dispersion force. Every molecule will have it because they are caused by a temporary dipole. So even though you are nonpolar, that means you're not a dipole, you can be induced to become a dipole, not forever, but temporarily. And this happens when molecules bump into each other. And imagine when they bump into each other, even though the electrons are distributed evenly throughout the molecule, when they bump into each other, you can imagine the electrons being shifted and somehow being all on one side. And because the electrons are being on one side, it's partially negative, and on the other opposite end, it'll be partially positive. So eventually, you essentially have a dipole. So you can imagine that you have a bunch of these nonpolar molecules, but for a split moment, they become a polar-like molecule. So they can be attracted to each other. The negative ends can be attracted to their positive ends, forcing this intermolecular force that we call dispersion forces. Although this force, because it's temporary, is very weak, does allow for liquids and solids to exist even for nonpolar molecules. Like the plastic that we talked about, plastic is basically made of carbon and hydrogen bonds, and we know carbon and hydrogen bonds are nonpolar bonds, so their molecule is very nonpolar. But yet it can still exist as a solid. And it turns out the reason for that is dispersion forces increases significantly based on the mass of the molecule. So in a plastic, it's called a polymer. It's actually very massive. So even though it is a nonpolar molecule, being so big of a molecule trumps it being a nonpolar molecule. You don't have to understand it at that level. It's something cool to understand. If you want to explore more, we can talk more. But the gist of this section is for you to understand that there are three types of intermolecular forces. We call them hydrogen bond, dipole-dipole, and dispersion. Hydrogen bonds are the strongest, followed by a dipole-dipole attraction, followed by the weakest is the dispersion forces. Hydrogen bonds occur only when you have a hydrogen connected to an oxygen, a nitrogen, or a fluorine, whereas a dipole-dipole attraction occurs when you have a polar molecule. When you have a nonpolar molecule, the only thing you have left is something called a dispersion force. Alright, so in today's lecture, it was a long one. By the end of it, you should be able to use VSEPR theory to predict the 3D shape of a molecule. And from the shape of the molecule and the polarity of the bonds, you should classify whether that molecule itself is polar or nonpolar. And lastly, you should be able just to describe the attractive forces between molecules. If I give you a molecule, you should be able to tell me what kind of attractive forces it possesses.